What's up, everyone? This is LeetCode 39, combination sum. We've done this problem in Python, now we're going to do it in C++. So we're given a distinct array of distinct integers, or I should say an array of distinct integers. And we have to basically find combinations that add up to 7, and you can use a number multiple times. But the combinations that you add to your output array have to be unique. Meaning, if we have a combination 2, 2, 3 that adds up to 7, we cannot include the combination 2, 3, 2 also once we include 2, 2, 3, right? Meaning the frequency of the numbers are the same in both, right? Like if we have 2, 2, 3, we have 2 2s and 1 3. Whereas if we do 2, 3, 2, we also have 2 3s or 2 2s and 1 3, just in different orders. So we can only include one of those, not both, because the combinations we add have to be unique. Okay. So I think this problem is not easy to implement necessarily, but to understand what you have to do, I think is easy enough in terms of the problem statement, right? Like what it's asking of you. The implementation is a little bit harder though, and that's because we have to use backtracking, which is a technique we have not encountered yet on the Grind 75 list. It's the first time I believe that we're doing backtracking, and backtracking shows up in a lot of problems. So make sure you use your resources and learn about backtracking. Not just this video, but just in general, like articles, YouTube videos, right? Because it is an important technique, and you're not going to be able to solve this problem if you've never used backtracking, because how do you even implement backtracking if you don't know how, right? So don't feel too bad if you can't solve this. I mean, it's kind of normal when you encounter a technique for the first time, right? Unless you're like a competitive programmer and you have some background, but at that point you would know what backtracking is, so it wouldn't be hard. So yeah, if this is hard for you, it should be, because we haven't done backtracking yet, right? So I'm going to kind of explain the gist of it, and I'm going to take this image from this article, from this person. So just to give him credit, this is where I'm going to get this image from that I'm going to use. Okay, so shout out to this guy. You can look him up, look up his name in the article name, and you can read through this if you want. So yeah. Now, his input, by the way, for his picture and example uses 237, whereas I'm using his image, but up here it says 2367, because I just copy pasted example 1. I just copy this, boop, and I paste it in here. But technically this isn't right, because his example is this input. There's no 6 here. But anyways, so we're gonna solve this using recursion, and we have a decision tree, okay? And I'm gonna kind of conceptually explain how we're going to handle backtracking and recursing and checking combinations and stuff. And you can think of it kind of like a tree problem. This is not a tree problem, obviously, but similar to a tree problem, right? You're going to basically go down certain paths, and then, you're going to do a DFS and check other paths, etc. Just like the tree problems we've done in the past on some of the easier tree problems, right? Just like a DFS on a tree. And that's kind of how we're going to handle the logic for recursing. Except to go a different path, we're going to have to change some stuff, okay? So, the way we're going to do this, right, is because we have a few things we need to account for. One of which is making sure combinations are unique, okay? So, initially we're going to start, so what this is right here, this array, this is not our answer array, this is our combination array. And this is basically building out certain combinations, and so that we can check if they equal up to target, okay? So for example, we're gonna go here and we can take a 2, right? And we can keep recursing on that index, so we can keep adding 2s, right? We can keep adding 2s, and at some point we're gonna have a combination, because either we're gonna have technically 3 cases. We're gonna have 3 cases, right? Our combination, one is our combination array does not sum up to target array, in which case we want to basically keep recursing if this doesn't add up to target quite yet. Or 2, case 2, it does add up to target, right? In which case, right, that would be a case like right here, in which case we will want to take this combination and basically append it to our answer array, right? Because this combination adds up to target. Or we have 3 where basically the combination is basically too big, right? So that would be a case like here, right? 2, 4, 6, 8. This is too big because 8 is bigger than our target, right? And so we basically have 3 conditions. Like, just think of it like that. Like, what are the conditions that would determine what we have to do, and whether we backtrack, whether we keep going forward, or whether we take what we're at, right? Think of it like that. And I'm just trying to break this problem down into smaller pieces so you can kind of digest it as a whole, right? As we start talking about this, okay? So we can keep recursing on basically the same index, the zeroth index. So we can keep adding 2's, right? And why do we keep adding 2's? Because they don't add up to target, right? These combination sums are too small. So we keep adding, and when we get here, this is too big, right? It adds up to 8, which is greater than the target. So what we're going to do is to backtrack is basically we're going to take this combination sum and we're going to basically go back up, except our combination sum is too big, right? Because we don't want this to. So we're going to pop this, right, from our combination array. And guess what? When we pop this from a combination array, we're back up here, technically, right? So now we can basically go forward one index, so we can add a 3, okay? So we can do 2, 2, 3. Well, that's also too big. So we want to pop this that we just added, go back up and add an 1 to the index, right? And basically do the same thing, right? And at some point, we're going to go here and we're out of bounds. So now we're going to basically go back up again. So we're going to go back up one level. So we're up here. And we just pop this 2, right, to get back up here. So now we want to add 1 to the index, and we're going to add a 3. So we have 2, 2, 3. And guess what? That adds up to target. Nice, right? And so kind of like a DFS on a tree, you can kind of understand how we're basically checking different combinations, right? Makes sense, right? If you've been following me on Grind 75, we've done a lot of similar things with tree problems. Now I want you to notice something. When we recurse on an index, we never go below whatever index we're on, right? Because what I mean by that is, like, when we go to this 3, you see how we either branch off to a 3, we add a 3, or we add a 7. But we never add a 2, right? You notice how we don't have 3, 2? That's by design, right? Because we don't ever want to check a combination like this. 3, 2, 2. That adds up to 7. But why would we ever want to check that? We check that down here, right? Remember, our combinations have to be unique. So we know for sure, because 2 is less than 3, and I believe that's the case always, because I believe our inputs are sorted. I don't know if it says that. But even if it wasn't sorted, let's say this 3 was here and this 2 was here, right? We wouldn't branch off to a 3 here, right? If this was a 2 and this was a 3, we wouldn't want to branch off to a 3 here, and we wouldn't if this wasn't sorted, right? If this was actually written like this, right? We wouldn't ever, when we're at this 2, right? Like, assume this is a 2, we wouldn't ever want to branch off to a 3 because it's below the index where we're at, or back an index, right? And we don't care about that, because we know when we were at this index, right? Let me go back to the original example, right? The reason we don't want to branch off to a 2 here is because we know for sure when we were here, we handled the case where we had a 3, right? Because is there functionally any difference for this specific problem between the combination 3, 2 or 2, 3? No, it's the same thing, right? So we don't want to check both, right? So that's why we only care about the index that we're on and the index above us, okay? Right? Because technically when we were back in index, we checked that index with the index we're on. So why would we want to do the inverse again and check the index that we're on with the index where we came from? We don't want to do that. So I hope that makes sense. That's just conceptually how we're avoiding adding a unique combination to answer array and doing it again later, right? It's how we avoid that problem. Because if you read this right here, that's what this is saying, right? Right? All this is telling you, right here, is you don't want to add like 3, 2, 2, and then later add I don't know, 2, 3, 2, right? Right? You don't want to add both of these to the answer array. They have to be unique. So you only want to add one of these. Okay. So yeah. So that's basically how we're going to do this problem. Okay. We're basically going to keep going, right, until we either have a number too big, or that's equal to target, or it's too small. in which case we keep recursing, and we keep going back up and basically backtracking and going different paths. This is a decision tree because, again, this is not a tree problem, but I hope you kind of understand conceptually how we're going to approach this problem, okay? So we're going to make a function. I'm going to call void. I'll just call it BT for, yeah, I'll just call it BT for backtrack. Okay. And we'll fill that out in a bit. So first of all, right, let's make our answer array. And I say array, but I mean a vector. Right, a vector of vectors, which makes sense, right? Because technically our output is an array of arrays, because we have a combination, and that's an array, and that's put into the actual answer array. Okay, and we have to return this because that's what we should be returning. Okay, and so we need to make a function called BT, which we did already, but we need to know what to pass to it. Okay, so we need to call this. So we know initially our combination array is empty, and we know initially we recurse at the 0th index and basically keep doing that. And as we go up, we add 1 to the index, right? So why don't we pass it the 0th index first, right? And why don't we pass it the answer array so we can do stuff with that. So we can append to it the candidates array so that we can use that to append to our combination array. And we're going to need a combination array, so we're going to say temp combo array, and let's make this up here. We're going to say vector of vector, and this is basically going to hold our different combinations. And if they add up to target, we're going to add this combo array into the answer array. Okay. And this is not an array of arrays, sorry. This is just an array, right? And so this array gets put into the answer array, which is why answer is vector of a vector. Okay. And we also need remaining, okay? And we'll just call it target. We need target, but up here we're going to call it remaining. Okay, so let's set our parameters first, okay? So we're going to have an int I, which is our index, right? We're going to have a reference. So our answer array is a vector of a vector. So reference. What's our next input parameter? Candidates. Candidates is our input, which is just a vector. Int vector int candidates. Right? We're going to now we have our combo array, so this is just a vector of an int reference array, and then we have int remaining. So let me discuss this really quick, and I'm sorry, you know, there's C++ is verbose, that's why I have to type slowly, make sure I don't have any errors. So let's handle array, or let's handle remaining, what this is doing, or what that variable is for. So the reason I have remain over here, by the way, is because the way we're going to do this is we're not going to build out these combinations and then add them up and see if they equal to target. We're basically going to know if we add up to target as we go. What I mean by that is basically initially remain, when we're first starting off initially, remain is initially going to be set to target, right? And when we add something, right? When we add something to the combination array, we're basically going to subtract that from remain, right? The reason we do that is because as we do that, right, at some point, we're going to have remain equals to 0. And that's how we know that we have a certain combination that adds up to target, right? Because we're subtracting what we're adding from remain, and it should make sense, right? If remain initially is target, and when we add stuff, we subtract that from remain. When that's equal to 0, it means that our combination sum should add up to target. Okay? So I'm going to write some comments out here as I write my code, okay? So this is our backtracking function, okay? This is really simple boilerplate setup stuff. Okay, now we're actually going to do the backtracking and all this stuff. So there are a few conditions we need to check, right? So we need a base case basically, which is if out of bounds or the combo array exceeds the target, return. Okay. Now, what that means, right, what this base case is going to check is if we go here, right, this is too big. If this is too big, we need to basically go back up. We need to backtrack, right? Because when we have a combination that's bigger than our target, right, 8 is bigger than 7, we don't want to keep adding, right? That doesn't make sense. So this is so when this is too big, we're basically going to return, right? So we're going to say, we're going to return, right? So that's one of our cases when we have to return when it's too big. And remember, when we backtrack and we go up, we basically want to go on to the next index, and we want to keep doing that. And at some point, we're going to also hit a out of bounds, right? In which case, that's when we want to backtrack from here when we go out of bounds, right? And so that's what would make us backtrack up also, so that now, instead of taking this path, we already checked these paths, so that now we can check this path, right? And this path. And then when we go up, now we can check this path and then this path, just like a DFS on a tree problem, right? So these are base cases to return, basically. Okay. Hope that makes sense. It should be pretty simple. Okay, so we're going to say if I, our index, is greater than or equal to the length of the candidates, right? Or, so if we're out of bounds in the index, that's a problem. Or the combination array exceeds target. And how do we know if combination array exceeds target? Do we need to add it up? No, we don't need to add this up. That's what this remain is for, right? So if remaining is less than 0, we know we have too many. The combination array adds up to way too big of a number that exceeds target. Okay. In which case we just want to return. Okay. Now we also have another case. Remember what I said earlier? There are 3 cases, right? There are 3 cases. Either the number's too small and we need to keep recursing, the number's too big and we need to return, right? So this is basically right here, right? This is basically number too big or out of bounds. In simple terms, that's what we're checking here, right? Now here is basically the case where and when I say number, I should say combination sum, right? Or sum of combinations is too big or out of bounds, then we return. Now here's the case where the combination sum adds up to target, right? So if remaining is equal to 0, we need to do something, right? What do we need to do if this adds up to target? Well, we need to put it to the answer array, right? We need to put this temporary combo array into the answer array because that's what we're returning, right? We're returning our combinations that add up to 7. Okay, so that's the case where we want to do answer.pushback temp combo array. Okay, so that's basically handle 2 cases. The number is too big or out of bounds. The number, and I say number, I mean combination sum. Number is too big or out of bounds. The number adds up to target, or the number is too small, right? In which case we want to recurse and keep going, right? So this is basically recursively go into the same index and change the remaining to account for the number we added, right? So we're gonna say BT, right? And let me just copy this, right? So I don't have mess up my variables or anything, right? Now let me remove these like types here. We just want the variable names, right? Right. So we were gonna basically recurse into the same index. So we're gonna keep this as I, not I+1, because this is a case where like when we're here, we want to basically keep using the 2s, right? Keep using the 2s. Okay. But when we add a 2, what we want to do is basically change, we want to append, so because when we're going here, we want to append this to our combination array because initially it's empty, right? So when we're at the 0th index, for example, right? Because technically up here, when we enter this here, when we're at this spot right here, we're at the 0th index already. So we want to basically add candidates at 0 so that we can have this combination array, our temporary combo array. Okay, so we're gonna say temp combo array dot push back candidates of I. Okay, so we updated temp combo array. We put as an input, but remaining also needs to get changed. So remaining is going to be remaining minus candidates of I, which makes sense, right? Because if remaining initially is 7, when we add this 2, well, remain shouldn't be 7 anymore. It should be 5, right? That's what we're doing. Okay. And then this is basically where we exit the call stack and go. We're going to exit the call stack, pop from the, not stack, but pop from the combo array and add the next index, right? So we're going to copy this. We're going to put this down here. Of course, we need to pop. So we're going to say temp combo array. And let me explain this. I know this video might be a little long, I'm sorry, but I'm explaining things step by step just so you understand what's going on, right? So what this is now, what we're doing now is, let's say we're here. Right, we basically recurse. Now, when we go back up the call stack, you know, because we're returning, we need to, this is in our combo array when we go back up, right? Because we added it, right? Before we pushed it, before we recursed. So in order to have this now, instead of this, we need to pop this number, right? Because if we don't do that, technically when we go up the call stack, and let's say we add a 3, we would technically have 2, 2, 2, 2, 3 instead of 2, 2, 2, 3, right? So we need to remove this last number when we pop this last number from the array when we go up the call stack. So that way, when we add 1 to the index, we have this instead of 2, 2, 2, 2, 3, right? We don't want that. We'd get incorrect answers. So that's basically what we're doing. We're not adding anything to the combo array because we just popped it, right? So we actually don't want to subtract anything also. So we want to keep it like this. Okay. Let me not forget my semicolons. Forget any. Okay. I think that should be it. Okay. Whoops, I forgot my E. Sorry about that. This is not pop, it's pop back. I'm not the best at C++. Tiny syntax errors. Let me see. Oh, sorry. I made a silly mistake. We're obviously moving forward in the index, right? When we go up the call stack, my error was stupid. It was like I was going here, I was going up the call stack, and then I was going back in. And I wasn't subtracting this either. I shouldn't. That's the right part. It's just that I was going into the same index. Silly mistake. Which is kind of the danger of copy and pasting, right? But I just copy and paste, so I don't have to write everything again. I'm just a little bit lazy, but it does bite me sometimes. So yeah, I think that should make sense. This video is a little bit long, but I mean, I did go step by step, so I hope this made sense. I think a lot of videos don't go step by step as they code, and it's a little confusing. But I did it that way so you know what every line does, what every conditional state checking does up here, right? And I wrote my comments too, right? And so, yeah, I hope this helped, and I'll see you in the next one. Peace out.